Hello, we are Espresso Patronum, Misha, Marianne, Dustin, Jack, and John. This is an exploded view of the coffee grinder that our team has decided to pursue for design for assembly and manufacturing. It's a hand coffee grinder designed to grind fresh coffee beans at various grind sizes in a portable form factor. Our primary customer group is made up of home baristas who brew coffee at home as either a hobby or a way to save costs on drinking coffee. Our secondary customer group are traveling coffee drinkers who want to drink coffee on the go and also appreciate the ability to grind their own fresh coffee beans while outside. The primary function of a hand coffee grinder is to grind coffee beans. In order to do so, the coffee grinder must contain or store the beans, crush the beans down into grounds, and then hold and store those subsequent grounds. In order to do so and crush the beans, the grinder must position the beans appropriately and then apply force to them in order to break them down. Additional functions of a hand coffee grinder include preventing injury to those handling the product, enhancing portability and cleanliness, and minimizing the effort required to turn or to grind the beans.
The function component mapping matrix. Here it shows the different functions and components. Again, they're going to be matched up with the fast diagram and the bill of materials for the actual correlation of the numbers. And on the side, we just make a note that the red X is meant to show the difference between the two customers, where the enhanced portability function is meant for the portable version, and that would be found under function 9, component 18. It's our functional differentiation table. We have the similar to both customers and different to each customers. The different is going to be the containing beans and grounds because we have different sizes of containers, so there's going to be different ways that they're going to be contained. The component commonality table. This remains unchanged from previously. Again, it's just going to be the lower trap will be the module between the two different customer groups.
In terms of our two models, we have the junior model with a smaller plastic trap and the king model with a stainless steel larger trap and a rubber bottom for grip. Both of these options share a common connection in order to make assembly easier so we can maintain one assembly line for longer. The assembly sequence, we can start with the main body, then go the grinder cap, the handle, then the drive shaft and the adjustment knob. Then go the burr carrier with the burr set, including the rotor and stator, and finally assemble the catch cup. The other assembly sequence that we came up with was the main body, then the burr carrier with the burr set, then the drive shaft and adjustment knob before we install the grinder top and catch cup. For our DFA manual analysis, we chose the platform part to be the lower trap retainer, as we found it was the easiest place for us to be able to split off the two models in order to differentiate them as late as possible. The module part, of course, is the lower trap, which represents the main difference between the two different models we have. And for our design for manual assembly, in order to improve it, we had 4 parts replaced by 1. The inner trap, trap casing, trap bottom, trap lock were all replaced by a snap fit trap as seen on the right. We found that we were able to change it from a twist fit over there in order to a snap fit. And both modules and the king size and junior size traps both connect to the same snap fit body.
When looking at the redesign for the lower trap retainer, we can see that the fasteners from the retainer lock and the retainer were able to be removed from the entire process, decreasing the assembly time and the manufacturing costs. As you can see, the assembly time drops by almost 65 cents, and the product function of the lower trap retainer still remains intact, and there can even be an increase in the retainer removal process.
In designing for the automated assembly, our team updated the Burr drive subsystem, and so specifically the drive carrier subsystem. And so in this design, the updates were adding a press fit to remove the screws, making the bottom part symmetric for easier assembly. And then burr alignment has been updated to 3 nodes rather than one, allowing for the beta angle to be 120 degrees rather than 360 degrees. So this process was updated because it contained parts found in high cost and high functionality in our quad chart. So moving into further details here. So the fasteners replaced by a snap fit are these fasteners here, and they used to screw through the bottom part into this piece, and now have been replaced by a snap fit that pushes into these holes in the bottom part. Now, then the second step is the second redesign is alpha symmetric part for ease of orientation. So this part seen below is symmetric on both sides. So the alpha angle is only 180 degrees, and whichever way it's oriented, it will work. So then it's easier to orient in an automated feed. And then lastly, there are 3 locating knobs seen here, and that decreases the stator burr alignment time by decreasing the beta angle of this part from 360 degrees to 120 degrees. And then here you can see the key dimensions of these features.
Is our actual cost analysis for design for automated assembly. Our original cost was calculated to be $4.03. After our redesign, we managed to save $2.81 per assembly and brought the final assembly down to $1.22. The selection, we talk about the 2 parts that we want to redesign. We went off the most important function and most important dimension. For the burst radiator, we decided the most important function would be the apply force, and the most important dimension would come from the blade grooves, so we decided to have a tolerance of 0.5 millimeters. For the lower trap retainer, we decided the most important function was to contain grounds, and the most important dimension will be the locking mechanism, so we gave this a tolerance of 0.7 millimeters.
When looking at the design for manufacturing for the per subsystem post DFA and post redesign, we can see that we use conventional milling for both parts and that our price decrease was about 70 cents per part. We will look at the DfM Pro 2 slides from now to see why this was. Additionally, when looking at the hubs quote for the burr subsystem, we can see that the quoted cost is $10.80. This cost is obviously very high, and it's because we're obviously going to be manufacturing in bulk when producing this product. Right now, this is for a singular product.
So as you can see, using DfM Pro, looking at the burst stator, we had to redesign standard hole sizes. So the burr did not have any standard hole sizes currently. It has partial holes, so holes that do not go all the way through, and flat bottom holes. And these are design issues that, in order to optimize the design, need to be fixed for future designs.
Looking at the lower trap retainer for our DFM portion. Post DFA, we were able to redesign it to significantly reduce the assembly cost. However, it ended up costing us 92.1 cents per part to manufacture it. However, post redesign, we were able to change some of the geometry to smooth it out and remove many of the harsh edges, which were significantly increasing the mold cost. These changes allowed us to bring the estimated cost to manufacture this part down from 92.1 cents to 35.
When looking at the PSS or the product service system, we made certain concerted efforts regarding our environmental efforts and, of course, the product service system. And regarding our environmental efforts, we made sure that the products we will be making will be using of recyclable materials that will not only be quality tested, but will again be better for the environment and better in case someone wants to throw out the product. And for the product service system, we came up with a way for local coffee shops to have incentive to leave broken grinders for a discounted cup of coffee. It encourages recycling from our customers, and a better product. In conclusion, we saved money on both the DFA manual, DFA automatic, and the DFM Part 1 and Part 2. Some critiques we have is that the DFA automatic changes may increase manufacturing prices.
So in the conclusion, if we were to restart, we had a few other ideas on how to apply it, on how to change the design to increase our ability to apply force to the coffee grinder. One of these ideas included having the handle be replaceable and removable in order to allow for the attachment of an electric drill in order to reach new customer groups, such as those looking for a coffee grinder on the job site, or any other areas in which a portable grinder that use power tools could be useful.